Morning, folks. Hey, congrats, seniors. A couple days away from this being this. We got tests on Thursday, lab on Friday. All right. So this is our in-class review. The test will be relatively short for you. We won't try to take up a ton of your time because I imagine that there are other classes that are also going to be having the same idea that we do. So, with that being said, I won't waste your time today. I'll get started. Remember, you can work on this with multiple people if you want to. Two or three is absolutely acceptable. Just make sure you show me some different font, all that good stuff. All right. First one out the gates. All right. So take a screen capture from O-Physics and add a picture of your own drawing of the following criteria: convex lens that produces a real image that is inverted. All right, let's go and see what we can find here. All right, so here's your simulation. Oh man, that's kind of cute. It comes up right away as a real image where all of the stuff goes together and also inverted. So what you would do is you would just take a screen cap of that. So the way I'm going to do it on mine is like this. Make sure that I get real image inverted. We'll copy that. We'll go to physics. Boom. Size that thing down. You get the gist of it, I think, right? Boom. All right. That would be a real image that is inverted. All right. Next one up. Virtual that is upright. All right. Virtual that is upright. Still using that so what we do is we grab the top arrow here and we start sliding. Now notice, as we slide that thing, that image gets further and further and further away, but all of a sudden, look what happens. There we go. All right. Once we go past the focal point, once we're at the focus, look at this now, right? If we're at the focal point, right, we start to see that virtual image is going to form for us. Everything looks pretty parallel, actually. So, all right. So what we do is we just slide this thing in here. All right, do the same thing. Boom. And we grab, oh, that's a bad one, sorry. That was a bad one. Something like that. And we get our image. Okay. Size it down for you. You get the gist of it. Okay. So just figure out how you can screen capture that. Whether that's if you're using an Apple or if you're using a PC or if you're using your phone, just draw a picture of it. Stuff like that off of the simulation. Okay. A convex lens is called well, for us here, a convex lens is called a converging lens. Okay? That is called a converging lens, meaning that it's going to converge on one spot. Remember, convex with the X on the end is going to make an X as long as you stay outside of that focal length. Okay, which we will. All right. Screen cap or a picture of a concave that produces a virtual upright. All right, so this one requires a little bit of a trick. All right, so concave, in order to get a concave, what you're going to have to do is you're going to have to grab onto this focal length here and slide that thing over to the other side. All right. By doing that, let me remind myself, what do I got to do here? Virtual and upright. Okay, virtual upright. All right, well, that did it for me. Okay, so I can take that object and I can move that any way, shape, or form, and that's going to be my picture that I need to have. All right, I can go outside the focus, I can go inside the focus, anywhere along there, anywhere along that image, or anywhere along that object movement, we're going to see an image that is upright and also virtual. Okay, different one, just slide it, move it differently. Okay, not too bad, hopefully. All right. A concave lens is often described as, that one is going to be diverging. That'll be a diverging lens for us. Okay? Because remember that as soon as that first one goes in parallel, it's going to shoot away from it based on the focal point. The next one, we're going to try and hit the focal point. It's going to shoot parallel through. The third one will shoot straight smack dab right down the middle of it. Okay? So, next one. We did that. All right. A Snell's law. A beam of red light from a helium neon laser travels through the air with an n equal to 1 and encounters a gigantic brick of diamond. That'd be awesome. N equal to 2.419. The beam of light enters the diamond at an angle of incidence of 35 degrees with respect to the normal. Calculate the angle of refraction inside the diamond. All right, I gotta go grab my calculator. Hold on 1 second. Oh, sorry about that. Forgot that was a necessary piece. All right, so what we have is that it enters the diamond at 35 degrees. Okay, so what that means for us is, here's what we're going to do. All right, so our N1 is going to be the air for us. So that's going to become 1.00 times our sine of theta now. Theta is going to be 35. Again, don't forget degree mode, right? That's going to be a big deal for us, right? This is 2.419. All right, so 1 times the sine of 35. The sine of 35 is 0.57. Glare out of there. There you go. All right. So 0.574 equals, or actually that's going to get divided by, sorry. So we'll take this, 0.5. You'll see what I am doing this in a second. Whoa, too much. All right, I guess we'll do it that way. Divided by 2.419. That equals then our sine of theta 2. All right, so divided by 2.419. All right. Get some light in there. All right, right. Paste it again. So sine of, so then what we got to do here now, right, is if we want to find theta, all right, so if we want to find theta 2, let me steal this part. So this is going to then be equal to, all right, let me get my function going here, sine inverse of 0.237. All right, I do that, and I find that theta 2 equals 13.7 degrees. Boom, boom, boom. All right, so that's how we're going to find that one. So again, we took n1 times sine of theta, divided it by 2.419, took the sine inverse of that, and we found that theta 2 in this case was 13.7 degrees. All right. Next one. So for this one, we've got a green laser with a N1, or an n of 1. It strikes a window pane or plate glass. The angle of incidence that it travels through the air at is 27 degrees. Then it is refracted in the window pane. So that's our angle of refraction at 17.3. What is the index of refraction for the window pane? All right, here we go. So this will be 1.00. Our theta here will be 27. Don't know my N2, but I know my theta 2. Theta 2 is going to be 17.3. All right, let's run some stuff. So what we end up seeing is sine of 27. So that's going to times 1 is going to be 0.454 equals N2 now times our sine of 17.3. That's 0.297. All right. To get N2, that equals 0.454 divided by 0.297. All right, let me grab that. All right, index of refraction for this one is 1.53. All right, so again, I took the sine of 27, multiplied it by 1, got 0.454, divided that by the sine of 17.3, and got my index of refraction of 1.53 for this one. Okay. All right, next one. All right, inexpensive diamond on a sketchy website. It claims to have a speed of light that is 1.39 times 10 to the 8th meters per second. If the speed of light is 3 times 10 to the 8th, what is the index of refraction for this diamond? All right, so, sorry, lost my, all right, so, here we go. All right, so, if we're using this kind of same idea here, what we know is that the speed of light itself is 3 times 10 to the 8th, right? The speed through the so-called diamond is 1.39 times 10 to the 8th. All right. So what we do, we're just going to take 3 times 10 to the 8th. Now, if you're using the caret button, again, you got to use parentheses in the bottom part. In fact, I'm going to put that in right now, just so that we make that a little bit more obvious for ourselves. All right. All right. So when I divided those two together, I found that this is 2.16 is my index of refraction for that. All right, pretty straightforward. No sine or cosine, or I'm sorry, no sine needed for this one or anything like that. All right. So since the index of refraction is 2.54, is this really a diamond? Well, according to the index of refraction that I found, because good grief, sorry. So because it isn't the same index of refraction, based on that, no, it's not a diamond. All right. So then it asks the question. So if it isn't a diamond, then how fast would the speed of light have to be? Well, okay, all right. So if I know that the index of refraction is 2.54, all right. What that means is this is 2.54. my speed up here is going to be 3 times 10 to the 8th, right? So now I don't have v. Okay, so what I'm going to do is I'm going to multiply both sides by v. So what ends up happening here is I get So I get 2.54 V. Steal this. Sorry. Equals that, right? All right. So then what I have to do is, in order to solve for V, I'm going to take and divide this by 2.54. All right. So that then should equal 3 times 10 to the 8th divided by 2.54. I find that I get 1.18 times. That's going to be 10 to the 8th meters per second. Okay? That's how we would find that index of refraction there. All right? Thin lens. Object is placed at 22. Image forms at 29. What is the focal length of this? All right, so when I'm looking for object, that's going to be my 22. My image is going to be my 29. So what we do here is we just start plugging them in. All right, now you could try and find the common denominator between these two. I chose to make this hard enough so that you wouldn't do that. So when I take the 1/22nd divided by 1/29th, I got 0.0799. Okay? Now, to fix all this stuff up, what I'm going to do is I got to get f all by itself. So that means I got to multiply both sides by f and then divide over, or I can just go ahead and take the inverse of both of these. What that means is basically I'm going to flip this thing. All right. So here's how this works. Ready? Watch. All right. So I'm going to take 1 divided by that. What that will do is that will clean this up. So if I take both sides and divide it by 1, or 1 divided by that, what ends up happening is that flips that f so that that thing gets on top as well. So this one, once I find that, all right, I find that this needs to be at the focal point or focal length of this is 12.5 centimeters. All right. Again, you can do inverse of that. You can do the reciprocal of it. All of those are going to produce the same exact answer for us. All right. Okay. Similar question now, but now we've got a focal point and we've got the object is placed there. Okay. So here we go. That. Copy that. So set up for us. We got 1/5. And we've got the object is placed there, so we've got 1/13. Okay. So what I'm going to do here is I am going to solve for 1/q. I'm going to take. Oops, sorry. 1/5 and subtract 1/13. So 1/5 minus 1/13. All right. So in this case, that then shows up as this is equal to 0.123. Okay. Again, this time I'll show you kind of how you can do the reciprocal of this. So I'm going to make this Q, because if I take the reciprocal of that, that will equal, let me get it up here, 0.123 to the -1. So if I go ahead and do that, now you can use caret button if you want. All right, I find my Q should equal 8.125 centimeters. Okay. All right, hopefully you're doing okay with that. All right, next one, angle of incidence. Identify the following points on the drawing. The angle of incidence is, now remember, this is the angle in which the light strikes, and it's always based off of the normal, okay? So my angle of incidence here should be B. Ooh, I gotta size that thing down, that looks gross. All right, so it should be point B. Now, the angle of reflection, also with respect to the normal for us, right, should be, which point do you think? Yep, you're right. That should be point C. Okay? All right? So angle of incidence and angle of reflection always are based off of that normal point. Okay? All right, to see his feet, Ray would need to look at which point here? He would need to look at, not point B, he would need to look at point C. Point D puts it too low. Point B is about the waist. All right. If we're looking to see the top of his head, then we're looking for point A for this one. Okay. All right. Screen cap of a following criteria drawing. All right. We want a concave mirror. All right. So let me get there. So I need the mirrors one. Sorry. All right. Okay, so what was our criteria again? We want a concave mirror, real image inverted. All right, real image that's inverted. Look at that. It gave it to us right off the bat, right? As long as that object is somewhere beyond the focal point, you're going to get a real image that's inverted. All right, so that's what that one looks like. Anywhere past outside of the focal point produces that. Okay, the next one. Virtual image that is upright. Okay, so with this one, we still want to use this concave mirror. So concave means that it's squished on in the middle. All right. So in order for us to get this, anytime we stay to the outside of that focal point, it does that. It doesn't do it for us. But once we go inside the focal point, look what happens. Right? Then we get that upright and virtual image. Remember, if we hit the actual perfect focal point, nothing happens. All right? Everything is going to be parallel for us. We'll never actually form a image together there. Okay? So anywhere inside that focal point produces what we want to get to. All right. Next one, convex mirror that produces a virtual upright image. All right. Convex mirror, what that means is that I got to slide my object past it. Now I'm going to see how this is a concave. That's a convex. Notice the change right up here. So here, I can go anywhere I want. Any size, any change, anything like that. That produces that there. All right. And then the last one says, hey, just produce a different one. Okay. So here again, all you're going to do is you're going to move that thing just all over the place, wherever it may go. Okay. That's kind of the review for you. If you have questions, zip me an email. Send me a direct message, anything like that. Otherwise, enjoy your Tuesday. We'll talk again and see you on Thursday. Good luck. Let me know if you got questions or anything like that, and we'll take care of those. All right? Have a good day. See ya.